Hello, this is David Hilster. I'm a critical thinker, dissident scientist, and if you are not science woke, then this is the place for you. There are literally thousands and thousands of scientists from around the world who have been working for decades outside the mainstream who have identified problems, fixed those problems, and who are proposing new theories and models. You're not going to find anything like this on the internet, so go down and click on that subscribe button in the little bell next to it, and you'll be alerted to when our next video drops. Well, I tell you folks, I've promised and promised and promised, and I'm just abusing my the good nature of this gentleman here today, who is next to me. You can see right here, who's Dr. Alexander Unzicker. I talked to him about him immensely. His book, the Figs Hake, I say that all the time. It's a spoonerism. The Higgs Fake is on my must-read books because we hear about particle physics all the time. We hear about billions of dollars being spent and all these science evangelists going on TV. And guess what? If you read this book, your eyes are going to be open. You're going to become more of a critical thinker, and you can make up your own mind. And maybe those thoughts of maybe things aren't so right in physics are actually true. And we're going to talk about some of those things now with my special guest here today, Dr. Alexander Unzicker. Welcome.
Hi, David. Hi again.
Well, I tell you, they've been waiting a long time, so I'm abusing. This is our third interview with him, and he's still sticking around. But we're going to talk about some really great subjects today. He's written three books, in fact: Einstein's Lost Key, The Higgs Fake, and also Bankrupting Physics, and is definitely a critical thinker. And he has interviewed, you go to his channel as well, it's called The Mach-In, or just look up Alexander Unzicker's I think you call it's Real Physics, right?
Real physics now.
Yeah.
Yeah, yeah, yeah.
How dare you even say real physics? But anyways, you want to check him out. It's great. He gets a lot of views, and rightly so, because he interviews some of the biggest supposed geniuses of our age in physics, and he's not afraid to ask the hard questions. And of course, his favorite opening line to his lectures online is, "For those of you who know what I'm going to talk about, I will give you a minute here if you would like to leave." And once in a while, you will hear a chair scraping along the ground, and a few people walking out, but most of them stick around because when he talks, a lot of people listen. So thanks so much for being with us today. And I want to talk about something that's really important, and it seems to be such a dichotomy. I mean, how could you get one word, right? How could you get so far away from what particle physics is today with this one word, and that's simplicity, right? I mean, obviously, if you even look at some of the interviews with David, what's David? Was he?
Dave Ross.
Yeah, he's American. He won a Nobel Prize for simplifying particle physics. But when you really look at and listen to these people, there's anything but simple. So tell me a little bit about your work really revolves along simplicity. To put it in, I guess, to start it out, we want to go towards simplicity, right? We seem to be going at the speed of light in the opposite direction. Am I wrong, or?
Yeah, yeah, yeah. I mean, it's not a secret. If you look at the standard model of particle physics, it has something like 20 parameters and 50 masses, something like 100 unexplained numbers. And cosmology is going the same way. We are about 13 or 15 unexplained numbers. It's definitely not simple, you know. And so people nowadays are saying, well, maybe nature is not that simple. Aren't you following an ideology if you claim that nature has to be simple? And what I try to say, I'm not personally worshiping anything. I just think there is evidence that good physical theories are simple, because that's what the history of physics tells you. And well, I just tried to give you a number of examples. That's the one obvious example is geocentric astronomy in the Dark Ages, and people were dealing with dozens of unexplained numbers and parameters. And when Newton's theory of gravitation came out, all these numbers were gone. Okay, you were left with just one remaining number, the gravitational constant. So, but there are dozens of other examples. Just I don't want to annoy you, but it's necessary that one remembers one of the key developments of physics. Take the unification of electricity and optics. Okay, it's in the formula electric constant times magnetic constant. It's 1/c², the speed of light. Wow, that's a big accomplishment. Why? Because it's a simplification. Before you had 3 constants, now you have only 2. That's the big progress, and that's the revolution in science. All the unification of optics and electrodynamics is there. Take Johann Jakob Balmer, who looked at the spectral lines of hydrogen in 1885. And he discovered the square of the natural numbers and condensed out of all these data, out of this bunch of spectral lines, he condensed one number. That was a big insight. That was a big simplification, actually. Instead of 3 dozens of numbers, he had just only one, the Rydberg constant. And now a second step, we're making fast forward in history 30 years. Niels Bohr explain that Rydberg constants in terms of other natural constants. Okay, so again, what's the key element of quantum mechanics? It's usually not phrased in this way, but that's the key element. You have a simplification. You explain Rydberg's constant by other constants of nature, and so on. I could give you in my book. There are a couple of another examples, but I think you got the point. The historical evidence is whenever we have a simplification, whenever we have fewer numbers, whenever we have fewer constants of nature, this is a big progress and this is a revolution. Yeah, and if we want to really advance physics, we have to keep that in mind.
Yeah, I think that's one of the things. If you look at a group like our group, you have people who are doing the exact same thing. Even with the particle physics today, they're taking. We have people, for instance. It's interesting that we have people in our group that will take, for instance, quarks and even the Higgs boson, and they'll look at the system there, give it some physicality, whether they're waves in an ether or particles or whatever, and they'll simplify it, right or wrong, right? If you look at the average person in our group, who is really a person who's a critical thinker, who's a person who is trying to advance science. I'm trying to find out what the universe is really doing. I'm looking at what's come before me, and they don't. You never hear. You don't hear them come up and say, I've got this great theory. It's way more complicated than. It doesn't even. It's not even. I think this idea of simplicity is so ingrained in those people who are in our group that now that I think about it, it's just hit me while you're talking. That's almost like you don't even discuss it, because it's almost an absurdity to these people who have already put themselves out on a limb, who are saying, I am going against, unfortunately, this, I may be in the majority of people, but I'm becoming vocal. I'm getting out there. I'm actually writing something down. I'm making a model. Oh my goodness. And it isn't the model that other people are doing, but there's always this idea that it's going to be a simpler model.
Mm-hmm, mm-hmm. Yeah, of course. I mean, if you're doing science, I mean, it's your job to find explanations. I mean, we have the fine structure constants. It's 137.03 and so on. But nobody's trying to explain that. I mean, Richard Feynman once said, every good theoretical physicist writes this number on his wall and worries about. But nobody of today's physicists seems to worry about. That's what worries me. We kind of, putting under the rug all these really interesting questions and dealing with the wrong ones. And if you're a physicist, it's your business to find explanations, not excuses that's because we live in a certain universe of a bunch of multiverses. No, that's not an explanation. So I would like that I would appreciate if physicists come back to these fundamental riddles, like the ratio of the proton and the electron mass. It's an unexplained number. And there are quantitative questions in a way, but there are even more profound conceptual questions behind. Yeah.
Yeah,
But I think,
absolutely, and I think what's really been gratifying for a lot of people who came to know you in the last couple of years from our group, somebody who, I mean, you don't see us sitting around interviewing Nobel Prize winners. We don't have that access. But I think one of the gratifying things is to see someone who says, "Oh yeah, we need to look at those things." One of the things is that when someone, for instance, somebody in our group who has a model, and there are some very good models in our group. I may not agree with them, but one thing I do agree with, they're better models. And one
mhm,
of the things is that they, a lot of our people, I have books behind me of people who've written entire books, and in those books, they go and they make sure they go, look, this constant is explained. Jeff Yee, he's a new guy. He has a energy wave theory. He's got it down to 4. He can
mhm,
explain the other constants. Now,
mhm,
to me, it's like, why are we using his model? Even if it isn't correct, even if it's we have to throw, I've talked about it with him. I said, even if we have to throw out the neutrino, if we have to throw out the W and Z particles, if we have to throw out the quarks, and maybe there are different things going on there, it
mhm,
still doesn't matter because
mhm,
in that
mhm,
model and in our group is this, like I said, this psyche of not only for the simplicity but these
mhm.
constants. So what is it about these constants? Let's talk more
Yeah,
about the
yeah,
constants.
I agree. I mean, I not necessarily, I do not necessarily agree with the particular model. Okay, it might be even
Exactly.
wrong,
Right.
but
Exactly.
what's right, definitely right, is the method. I mean,
Yes. Yes.
I'm happy about everyone who tackles at least the big questions
Yes.
instead of instead of talking around. I
Yes.
mean, and that's the way we have to deal with the problems, and we have also to deal with a different method because a lot of non-mainstream scientists are criticized because they have different methods because there is so much calculating in theoretical physics, so much certain type of mathematics. I'm not against mathematics, but not the way they do it, But again, if you look at the history of physics, there is always a mathematical part of a theory. Of course, Newton's law of gravitation needs the inverse square law, but it's not the key how everything started. Almost every scientific revolution has a conceptual idea before the math, before it goes to the math. You
Hmm.
know, I mean,
Sure.
Newton knew it was wow. Couldn't it be that earthly and celestial gravity was the same origin? Wow, that's a really great idea. Or Niels Bohr, who said, "Oh, we have this constant of nature, h bar, which says something about the energy of light. Couldn't it be relevant for atoms?" That was a
Hmm.
spectacular thought, but a very simple, intuitive way to look at it. Had nothing to do with mathematics. Okay, or it took. These are the revolutions that actually happened, but there were other thoughts which are not realized, like Ernst Mach, who said,
Hmm.
well, let's look at the gravitational constants. Wouldn't it make sense if the strength of gravity is related to the presence of other matters in the universe? Wow, that's a really encompassing, intelligent vision of gravity, and I miss that kind of methodology. I miss that kind of thinking big, if you want. I miss that kind of intuitive, non-mathematical
Hmm.
uh, thinking in the contemporary fashions. Yeah.
Yeah, absolutely. And I think that's why our group has been thriving in the sense of people do look at that. One of the things people who is there's a Dr. Andrea Cis from Brazil. My wife's Brazilian, so I have a connection
I
there.
know. Yeah.
Yeah, and he actually teaches he doesn't teach Maxwell. He teaches
Mhm, mhm.
Ampere, and
Yeah, that's
he
interesting.
teaches
Yeah,
he
it's
teaches
really interesting.
Yeah,
Yeah,
and he teaches Weber, and he was, and I noticed in your book, I was going through it,
yeah, yeah.
your book. I think
By
it
the
was
way, you know that it was Weber who discovered the formula of c squared equals 1 over the electric. It was Weber's idea, yeah.
yes,
And he
yes.
Assis is taking on these old ideas of Weber. Very interesting, yeah.
Yeah, and then you had also, I saw in your book, I'm not sure which book because again I read all three getting ready for this today, but you talked about Newton's bucket, and what is Newton's bucket is, well, if you know rotate a bucket around your head, for instance, it'll stay, or if you spin a bucket, you get this elliptical kind of thing going on. And what does that happen? And Andre C said something a long time ago when I first started this. I got into this in 1992, the meeting critical thinkers like yourself and that. And
Mhm.
he said something that I just thought was ludicrous. I mean, he says, "No, my feeling is the reason this happens is because of all the mass that's here in the universe." And I'm thinking, that's crazy. What does that have to do with anything? And then my dad and I end up uh, coming up. He has a solution to how particles and waves. You can get waves from particles. There's no such thing as photons. To him, he came up in 2015. You have waves of particles. That is, waves have to have a plurality of particles. So we started working at our model, which is all particles and all Newtonian. And we were finding you can describe all the universe so far you can, but we ended up saying, he goes, oh, he's turned to me and said, Dave, you know where all the graviton particles are coming from? And again, this is a graviton model, right? And I said, no. He says, all the suns, all the mass. And I go, I've heard that somewhere before. And so what's really, I think what's really great about the group we're in is you
Mhm.
have all these people, like you said, thinking at a fundamental. They're not thinking about, oh, the mathematicals, because one of the things I notice, one of the things I don't like about special relativity, and even the people who I do think there's problems with it, I'm not, Dr. Karazani found some, but what happens is, and even with general relativity, you get into the mathematics and you play mathematical games. You start to get into the mathematics and you forget, like, what does this mean physically? What are we talking about? Have we lost the recipe? Have we lost why we're doing this? And I think that the whole methodology that you're talking about in the group that we have actually does that. And I think when you talk about, I wish we could get back to that, right or wrong, like me.
Mhm. Mhm.
I don't agree with everything I read. There's things in the book, your books, that I said, wait a minute, I actually think that maybe it's something else. But it's the debate, it's the thinking of something else. It's actually having those place to stand on, that our criticisms in our group don't come from, well, your upness, it needs an adjustment on the parameter, the variable, and I can have some grad student write about that. No, we're saying, wait a minute,
Mhm.
does that violate, even why we're even doing this? Should we even throw this whole idea out? I mean, those are the kinds of conversations that I think is, like you're saying, it's the methodology that, in my understanding, you're saying that the methodology today has really, it revolves about really small tweaks on something when maybe we've got to do some major changes. Is that some of the things you're talking about when you talk about methodology, or
Yeah,
am I off?
I think so. I might disagree a little bit with the mathematics of special relativity, which I don't think is so misplaced. Anyway, I think you're completely right that people today are playing mathematical games completely disconnected from reality. But don't let's go into that too much. I think what I mean, you at a certain point to make quantitative predictions, of course, you need mathematical formulations. I'm far from. I'm not against mathematics at all. I
Sure,
mean,
sure.
on the contrary, I think the real deep problems of space and time we might only resolve with a very interesting mathematics of the three sphere or something like that. That's what I personally now I try to study in mathematics. But what we have lost the ability to ask the simple questions. Why? And as we mentioned it, why there is gravity? Okay, why is the universe related in this strange manner to the strength of the gravitational constants. Why there is something like relativity? Does anybody ask that questions? Couldn't you just build the world without that radioactivity? Who needs that? Who on earth needs spin? It just, if you look at conventional physics, it's just annoying, complicating stuff that spoils your equations. That physics would be nicer, so to speak, without that strange spin. But no, I mean, if you're doing physics, you have to find explanations. You have to find a priori reasons that necessarily predict the phenomenon of spin, of gravity, of radioactivity, and so on. And well, I'm really struggling with these kind of questions, and right now my focus is on the concepts of space and time. But well, maybe that gets too long as an answer, and you comment on.
No. In fact, that brings us into our last topic of this session, which is space-time. A lot of our people in our group look at space-time and saying, well, there is stuff in space. What is it? You hear space-time, you hear the fabric of space-time. You hear the space-time foam, this kind of quantum foam that comes and goes. You know, and obviously, if you bend something that is, if space-time was there and it bends, how could you bend nothing? Space is sort of a place where mass is. Time has more relate to movement than it is a thing. How could you then put them together and bend it? So one of the things is that in our group there's, you know, ether, there's particle, there's lattice, there are different. People are saying, you know, again, I'm not here, like you said, we're not here to argue those points. That's why we have our conferences. That's why we have our society. Those are the places to argue those points, and those are the things to argue. But, you know, they don't look at, you hear about space-time. What, can you tell us a little bit about what is it exactly from your perspective? What is space-time in today's, because we hear about it and we read about it and it's so crazy to us. What's in their heads are thinking, and what should we be looking at? Because that's one of the things you said you're interested in are looking at.
Space-time is a misconception. I think it's a misconception. There are a couple of arguments which bring me to that conclusion. I mean, the first one is, if you start, as I mentioned earlier, reflecting about physical constants, and you say the less physical constants you have, the better your theory is. And at the very end, you want to do without any physical constant, okay? But it turns out it's very, very hard to get rid of the speed of light and Planck's constant h. So you really hit a wall because you need these two constants whenever you want to talk about space and time, about meters and seconds, okay? So I wondered, what's the problem? Can we go even deeper? What's the real problem behind it? And I think the real problem is Newton. Newton was the founder of modern science, but he started from the concept, there is three-dimensional space, we don't question that. There is time, a one-dimensional entity, we don't question that. And that might be wrong. It might be that space and time are just the easiest way to perceive reality for our human brains, but it's not the most adequate way to deal with reality if you look at the fundamental laws of nature. Why I'm saying that? At the very end, these two constants, the speed of light and Planck's constant, are anomalies. Okay? From Newton's theory, there is no reason whatsoever that masses should not be accelerated beyond a certain limiting velocity. Why is this limiting velocity? Please give me a reason. There is no reason. So special relativity, it's very nice. I'm not criticizing it, but at the very end, it might turn out that it's just a workaround around the real problem, which is there is this phenomenon of a limiting velocity, which Newton did not predict. And for that reason, it's an anomaly in a Kuhnian sense that should have falsified the very concept of space and time. And instead, people are postulating a parameter, which is c, and say, okay, special relativity, we got it fixed. That's one thing. And the next thing happened with the discovery of Planck's constants, which came as a total surprise to the physicists of the early 20th century. And it revolutionized physics. It's said to be a revolution. But at the very end, we have introduced another free parameter, another something which is unexplained, and just to fix things, okay? And this might be the real problem. The speed of light is one thing, and Planck's constant is another thing, and these two anomalies should make us doubt about the validity of space and time, rather than thinking about a unification of quantum physics and relativity, which is not possible and everybody talks about. But that's formulating, I think, the problem in the wrong way. The real problem is we haven't understood space and time. And physicists instead have been glossing over that problem for a century. And I think it's if you look back at history, I think it's one of the most catastrophic developments in physics that since 1908, when Minkowski held his famous speech about space and time, I think it's a complete misconception to talk about a four-dimensional space-time, because it's not the same thing. You can't just link spatial dimensions to temporal dimensions. And people are saying, oh, we just have a conversion factor, which is no. I mean, if you say that space is the same phenomenon than time, you're literally denying reality. Okay, and this is what physics doing. What physics is doing, and I think we must really question that and maybe discover some mathematics that necessarily bring up these constants H and C from first principles. That's what I think.
Very interesting. And actually there is, hanging out with these people, there is a possible answer to one of your questions on the speed of C, and that would come from Dr. Glenn Borchert, which is infinity, which is you can never have the idea that I subscribe to as well, because I can't subscribe to the idea of a fundamental particle, because if you have a fundamental particle, then you have, Unzicker at its best, which is a very interesting package with very interesting attributes that all of a sudden will organize itself. And so with this thought of infinity, meaning that if you have the speed of light, let's say if they're photons and they're traveling, that the reason they're traveling at c is because there's a level down and there's a level down below that, and those things organize each level. So what we're really doing at the speed of c in an infinite universe, in that sense, not up and down, is that you're going to say, well, I'm going to use it to see because it's convenient, because if I sit there and then have to explain all this below that and say, yeah, well, I can explain why it's there, but why I'm going to do calculations with that, it's just not feasible to do that. So for those people who know my channel, I talk about the infinity, and that is a different, like you're saying, it's a wholly different perspective. And so I agree. I think really what you said is I think there's a gut feeling. People have that same gut feeling. How is it that you have these things that we call 3 X, Y, and Z, and then you have something T, which is this completely different concept? And now I'm going to make it, because I have using language. One of the things, because I've got a master's in linguistics, I try to get computers to understand human language. Well, I try to understand human language, and we have a reason we have these things. And just because we have a dimension and we have 3 of them doesn't mean there are 4 of them, at least in our system. You can't just say, I now have 5, I have 6, and I'm going to label it this. It's just like, that's Harry Potter. This is magic. And so I think it's very profound what you said about, we just can't do that. And if you do it, I think the profound thing you said is that once you get outside of that, I mean, once you do that, you're not in the same system anymore. You can say what you want, but people say, no, I'm in the same system. I just found it's different, and they think they are clever. And I think that's one of the places, because my bachelor's is in mathematics. I love mathematics. But even our real number system, one of the things that is interesting on the real number system side, and my dad came to the same conclusion with our model, is that there are no negative numbers. Negative numbers exist because of our system. If you go to find a negative number in the universe, you don't have them. So we have to understand that even our mathematical system is
good question. Yeah.
So, but anyways, I think we've come to our I think the end of this session, because again, if I keep going, my wife is going to come home and bash me on the head, and I'll be here.
Yeah. Just a final remark. Well, I think we actually asking a lot of wrong questions. Also, dealing with everybody talks about light, waves and particles. What's right? What's wrong? No, I think the more basic question is why we have these very distinct, two very different phenomena of light and matter. One is related to C, the other is related to Planck's constant. That's the real basic questions, and that brings us to question the concepts of space and time. But I must say, I mean, at this point, it becomes incredibly difficult, because you're literally losing your basis. I mean, if it goes even to language, the concept of space and time is so interlinked with our everyday language. We would even have problems communicating and talking about such a new theory, if it exists, that in one day might replace the concepts of space and time with something more adequate for describing reality. It's just really, really difficult.
Yeah, and it gets us to another thing, that what we try to do within our group is vocabulary, right? We have to understand that the words we use are powerful and can be deceptive at the same time. And I think one of the things in our group, for instance, it took us many decades to understand that energy is a concept. It is a fundamental concept for us to do calculations. It's really important. But a lot of people are saying, no, what's more important to me is work, and I can just, express that in a different way. So even just the language we use is important. And in the word space-time has taken on this a life of its own, where I think people who are critical thinkers, people who are really just trying to find out the way the universe works, we're getting space-time to death, and I think it's time that we stand back and say, ask some maybe different questions. But anyways, we can ask questions all day long. I want to thank you so much. Our guest today is.
Let's conclude that. Yeah. Thanks for contributing to bringing physics back to its real origin, which is natural philosophy.
Yes.
Okay.
Yes.
These are the real questions, and it's a different science. Let's try to bring it back there.
Yeah. And in fact, our new website that's coming out, which you guys want to stay tuned for, Dr. Alexander Unzicker is going to be part of it. He's really a great science writer. I look forward to having some articles from him. But on there, I created a very simple concept, and that is, we as human beings want to be science woke. We want to be woke to science, what's going on. We want to be critical, and how do we do that? We become critical thinkers. And where do we do it? Where's the house that we live in? That's natural philosophy. And so that's what we are going to try to do here. And I want to thank all of the subscribers out there, all the people who have. If you haven't subscribe to Dr. Alexander Unzicker's YouTube channel, The Machian. Great stuff. You want to go there and take a look at it. But let's keep this idea alive. And remember what I always say: to everybody all the time. Stay critical, stay thinking. I'm Dave D. Hilster. I'm your science therapist trying to get you to the promised land of being science woke, and with people like Dr. Alexander Unzicker and his books like The Higgs Fake and Einstein Lost Keys. My headset falling down on me here. You certainly can get in that direction. Thanks so much, and ciao for now.
Okay. Thank you, David. Goodbye.
Thank you. Bye-bye.